Electromagnetic waves in outer space travel at a speed of 300,000 kilometers per second. This is the same for radio waves and gamma rays. So, is the speed of radio waves or gamma rays the same through transparent glass or water? The speed of electromagnetic waves in transparent media. In a vacuum, electromagnetic waves, including radio waves and gamma rays, travel at the speed of light, which is about 300,000 kilometers per second. However, the speed of electromagnetic waves in transparent media, such as glass or water, is not the same as in a vacuum. The speed of electromagnetic waves in a medium depends on the medium's refractive index. The refractive index of a medium is a measure of how much the speed of light is slowed down in that medium. A higher refractive index means that the speed of light is slower. Glass and water have high refractive indices. This means that the speed of electromagnetic waves in glass or water is slower than in a vacuum. Radio waves have longer wavelengths than gamma rays. In general, longer wavelengths are less affected by the refractive index of a medium. This means that the speed of radio waves in glass or water is less affected by the refractive index than the speed of gamma rays. The speed of electromagnetic waves in a medium can be calculated using the following equation. V equals C, N, where V is the speed of the electromagnetic wave in the medium. C is the speed of light in a vacuum, 300,000 kilometers per second. N is the refractive index of the medium. For example, the refractive index of glass is about 1.5. This means that the speed of radio waves in glass is about 200,000 kilometers per second. The refractive index of gamma rays is about 1.00000000. This means that the speed of gamma rays in glass is about 299,999,999 kilometers per second. In general, the closer the refractive index of a medium is to 1, the less the speed of electromagnetic waves is slowed down. This means that gamma rays, which have a refractive index close to 1, travel at speeds that are very close to the speed of light in a vacuum. For example, the refractive index of glass is about 1.5. This means that the speed of radio waves in glass is about 2/3 of the speed of light in a vacuum. However, the refractive index of gamma rays is about 1.00000000. This means that the speed of gamma rays in glass is about the same as the speed of light in a vacuum. Therefore, the closer the refractive index of a medium is to 1, the more closely the speed of electromagnetic waves approaches the speed of light in a vacuum. If it is assumed that light or electromagnetic waves move as waves, the trajectory of the gamma rays is actually considered to be much longer than the trajectory of the radio waves. Then, we come to the conclusion that the distance traveled by electromagnetic waves in outer space is not all 300,000 kilometers. Is that correct? Yes, that's correct. Assuming that light or electromagnetic waves move while drawing a waveform, radio waves have longer wavelengths, and gamma rays have shorter wavelengths. Therefore, radio waves have more wave cycles compared to gamma rays. In other words, radio waves cover a greater distance over a longer period compared to gamma rays. Since the speed of electromagnetic waves in space is the same as the speed of light in a vacuum, radio waves cover a longer distance than gamma rays. Therefore, the conclusion can be reached that the distance traveled by electromagnetic waves in space is not consistently 300,000 kilometers, but it varies. Of course, the assumption that light or electromagnetic waves move while drawing a waveform is an approximate explanation. In reality, light or electromagnetic waves exhibit both particle and wave characteristics simultaneously. Therefore, to accurately measure the distance traveled by light or electromagnetic waves, both the particle and wave properties must be considered. However, in typical situations, the assumption that light or electromagnetic waves move while drawing a waveform is sufficiently valid. Therefore, the above conclusion can be considered valid in general situations. If we assume that electromagnetic waves move while drawing a waveform, radio waves with longer wavelengths will have much longer trajectories compared to gamma rays with shorter wavelengths. This is because longer wavelength electromagnetic waves have a longer vibration period compared to shorter wavelength waves. For example, let's assume the wavelength of a radio wave is 1 meter, and the wavelength of a gamma ray is 1 centimeter. In this case, the radio wave will cover 300,000 kilometers in 1 second while vibrating 300,000 times. On the other hand, the gamma ray will cover 300,000 kilometers in 1 second while vibrating 3 million times. Therefore, the radio wave will vibrate along a 1 meter trajectory in 1 second, while the gamma ray will vibrate along a 1 centimeter trajectory. As a result, the trajectory covered by the radio wave is 100 times longer than that covered by the gamma ray. For this reason, the conclusion can be reached that the distance traveled by electromagnetic waves in space is not consistently 300,000 kilometers but varies. Of course, the assumption that electromagnetic waves move while drawing a waveform may differ from reality. Electromagnetic waves exhibit both wave and particle characteristics. Therefore, when calculating the distance traveled by electromagnetic waves, both wave and particle properties should be taken into account. However, in general, it is common to make the assumption that electromagnetic waves move while drawing a waveform. Therefore, based on this assumption, the conclusion can be reached that the distance traveled by electromagnetic waves in space is not consistently 300,000 kilometers but varies.